Okay, let's talk about something less complicated. So I would like to talk about formalization. In HoTT, so HoTT is homotopy type theory. Hoping everyone is, well, let me say it anyway. Okay, so this is something that I'm glad to say I do for a living, right? Very nice. Some of you are experts on homotopy type theories. For example, Steve is here. But some of you are not, and I appreciate that. So what I want to do in this talk, I want to give an example of something very practical, something that arises when you take the system and you start formalizing mathematics in it, and then there are certain things that are just like kind of tricks or techniques that are known to someone who has some experience doing this, but are not known to newcomers, okay? And I want to sort of elucidate this point and really make this very explicit and spread the word a little bit. Because a lot of these things are kind of lost in, you know, they're in someone's head. Like, if you want to do something in Lean, then you ask Mario, like, oh, how do you do this? But if Mario's not around, you're lost, right? And so it's hard to pick these things up just by looking at code or through osmosis. It can be done, but it would be good if we talk about this more. So that's going to be my attempt here, okay? Right. In particular, okay, so one of the things I do is I don't just formalize any sort of mathematics. One particular thing I do is I like to formalize synthetic homotopy theory. And if time permits, which I think it will, I will do an example at the end, and it will be self-contained. Okay, so you don't need to know anything about this. Okay, now...
Maybe you want to say what synthetic means.
Right, okay.
Because that's been...
Yes, let me give a 2-second explanation, because I mean, this would be a topic for a week, I would say. But somehow, what HoTT allows you to do is it allows you to think of these as your basic objects or your types as spaces up to homotopy. And it's synthetic in the sense that you don't need to manually build these spaces. They're just already spaces out of their own. So the basic building block is like the immediate thing you work with. I will also give examples of this, it will become clearer. Okay? So I want to get to the basic problem. The basic problem is extremely simple.
Can I interject something?
Yeah?
Maybe as opposed to analytic, which is a
Yes.
set with a topology, and then factoring out my own abilities.
Right.
That would be the alternative.
Yes.
Homotopy theory intrinsically. The types are homotopy types.
Exactly. Okay, so the problem is you're given a map, let's say F, from X to Y, and show it's an equivalence. Okay. This is extremely common. When you want to do some formalization or you want to do some mathematics, this is like a very typical problem that you encounter. And that you have to do this. I mean, you can kind of treat this informally. If you don't know what it is, you can kind of think isomorphism. But it's not too important. I'm going to be light on the mathematical definitions, okay? Okay, so there's several approaches to how you might do this. And I want to sketch 3 of them. And sort of in increasing order of goodness and also in increasing order of how I learned them, okay? So, like approaches to this. Okay, so approach number 1. If I ask you to show that this map is an equivalence or an isomorphism, what do you do? Someone who's not an expert, give me a suggestion, please.
Inverse.
Right, exactly. This is if you ask someone new how to do this, that's what they're going to say, right? So the first approach is to say, okay, I construct G, which goes in the other direction, right? And I show and I prove that if I do F first on a little x, and then G, then I get X, and well, the other way around, right? Okay, for all X and Y. Nothing wrong with that, and you could do it, but the point is that in formalization, convenience matters. Right? So it's not so much about that, the fact that you might be able to do it, but maybe it's the number of lines or the number of hours you're willing to spend on this. And so this is maybe not, not the greatest thing. It could be that it's still quite convenient to give this map, maybe, right? Or maybe it's not super convenient, but you can do it. But then you have to prove these equalities, and then maybe you have to actually do some calculations, and if you are a bit familiar with dependent type theory, then you know that you might get some transports in there, and you have to really think about this, and it becomes complicated. Okay, so that's usually not very convenient. So often not convenient. And now on paper you might cheat a little bit, and you say, yeah, one can prove that this is an inverse, right? Exercise left to the reader, and then you move on. But if you formalize, then you have to be honest. So, okay. So often not very promising. So what's the second approach? The second approach, which works surprisingly often, I would say, is to reconstruct F as a series of small equivalences. Let's say like smaller equivalences. Right, so you start with X, and then maybe instead of going directly to Y, you go into some A1, and you have some, you know that this map is an equivalence, and then you go down here, A2, and then maybe another one, A3, and then finally you go back into Y like this, okay? And then you have F here. I can give some examples of what sort of equivalence you might be thinking of in just this, well, maybe I give those first. Right? So, some examples, such small equivalences. The point is that they're really, really basic, but you kind of reuse them over and over again, right? Like little Lego blocks, I'd say. So, so one thing would be if you have some type A, and then you have B, which is a family of types over that, and then you have C, which is a dependent thing over this. So B takes one parameter A, and C takes two parameters in A, and then a B at the appropriate index here. And then you show, for example, that if you look at this dependent, well, you're going to build this type where you first collect A's, now you're going to collect B's, and then you're going to collect stuff in C. That's the same thing as like sort of taking this component at once, right? This sort of thing. It's just like some sort of dependent curry, right? There's really not much going on. Like I said, it's a very basic equivalence, but it's surprising how much you can do just building up this kind of machinery. Another very sort of HoTT-like example is this one, where you have an element of your type X, and you consider the type or the space of all elements in X such that X is equal to Y. That as a whole type is actually just the single point. And this gets used like so many times, it's incredible, right? But it's extremely basic, but this kind of thing, I will give an example at the end, okay? But this is the sort of thing you should be thinking of. You just chain these things together, all okay. Does that make sense so far? Okay. Now, I have Yes, please.
When you are doing this formally
Yeah,
in the proof assistant, like when you're just hand waving,
yeah.
you can still use this. You just look at a part of the formula and you say, oh, this is obviously just the identity, and you replace it. But is there a particular order in which you need to do it when you are programming, like from outside in, or is that an issue?
You mean if this is some complicated expression that you want to...
Some complicated expression and you see that in the middle.
Right. Maybe. It could affect a little bit how things are actually compute down. But I'm precisely going to get to this now. So hopefully it will be clear. Let me know if it's not any clearer. Okay. Because so I said I'm going to reconstruct F as these series of the small equivalences, but there's a small proof obligation here, which is actually that if I take this round trip, I get my map F back, right? I mean, over here, a priori, I just have some equivalence, but there is an obligation here to actually prove that the diagram commutes, right? That I actually reconstructed my original map F. Because the point of the problem is not so much to show that there is an equivalence between X and Y, it's showing that this particular map is an equivalence. Okay. And so, this maybe holds definitionally, right? So you put it in the proof assistant and you say REFL or compute, and it says, yeah, that's fine, but maybe not. And then, if not, then you're kind of back into this situation here, right? Where you have to actually check some equality and it might get painful. Okay. Now, surprisingly, I sort of only use this technique all the way through my PhD. So you can I'm the living proof you can get a PhD by just doing this, okay? But you can do a little bit better, because then I became a postdoc and I learned about this, right? So, okay. So for the third technique, you use a small fact about equivalences, which is that equivalences satisfy 3 for 2. Okay. So what that means is that, so if, let's see, let's do this. So if you have a diagram that commutes like this, right? Then, well, if any two maps are equivalences, then so is the third. Okay, it's a basic fact. You prove about equivalences once, and then you get to use it. The point is that you can then create this kind of situation, but you reorient the diagram in such a way that it is convenient for the commutation to hold definitionally or almost definitionally. And so then you don't need to worry about reconstructing F as such an equivalence, but it's like F after some other equivalences, but that's completely fine. And it actually works out quite well in practice. So it's a small little tweak of this technique. Okay? So you might have like F going here, and then maybe you go down, because these are equivalences anyway, right? So I might as well just invert them like this, and then maybe here into A2, and then A1 here. Right? Maybe I prefer to set things up this way. And very often, what I find in the examples that where I use this technique is you have some projection maps, which happen to be equivalences. Now, in a very real sense, because the map is an equivalence, it can't really forget any information, right? Because it's, I can go back. So in some sense, there's no forgetting the information. On the other hand, there is a direct computation, and if I project, then I am, in some other sense, I am forgetting stuff, right? In a more definitional sense. And so what I end up doing is I point the diagrams in such a way that all the projections are facing out, right? So in a definitional sense, I'm trying to get rid of as much information as possible so that in the end, my type at the end is as simple as it gets, and the equalities there is as simple as they get. That's the basic idea. Okay, are we still on board with this? Some people are not. Okay. Did I answer your question, by the way?
No, but
Okay.
it's okay.
Okay. At least I've managed to get your attention. Anyway,
You distracted me, so
I see. Okay, I successfully distracted you, and now I'm getting back to it. Okay. Let me try to illustrate this idea with an example from synthetic homotopy theory that hopefully brings all of this a little bit to light, and also as a benefit, you get to learn a little bit of this, and you get to see what it looks like. Okay. So if my counting is correct, I will give you several pictures and only one definition. Okay, so I'll try to keep this as a very intuitive. So let's try to do this. Okay. So the point or the statement that I want to prove is the following proposition: suspensions, and I will explain this in just a second. Suspensions increase connectivity. That's the statement that I would like to prove. Okay, so I have to explain two things: what are suspensions and what is connectivity. Okay. So for the suspensions, I could give a formal definition, but I'm going to draw a picture. Okay. So if we have some type X, then I describe in a picture the suspension of X for you. Suspension of X. Okay. Okay, so confusingly, that's also denoted sigma X. Okay, but there will never be a subscript here, so there's no possible confusion, because for the other ones, I will never drop the subscript. Okay, what does this look like? It is a new type, which has two distinguished points, which I draw like this, and I label them north and south, okay? And then in between, I picture my type X. Now the operation that you do is for any point in your type X or in your space X, I'm going to add a path or an identity or an equality from north to south. Okay, and so if I have another one here, go down like that. Yeah. Of course, I have to do this in a reasonable way. So in the sense that if I go down using this path through X, and I go back up by reversing the path through X, then that should be the same thing as just staying put at the North Pole, okay? So in some sense, you're adding these paths freely, and you can make all of this precise using so-called higher inductive type, okay? But the picture, in many ways, is good enough to keep in mind.
So if you go from north to south using X and go from south to north using Y, you do not want this to be an identity.
No, unless these points are actually equal, right?
Yeah.
Yes.
And do you add the paths that you add as the constructors or whatever is that from like north to X, X to south?
So you only for any point in X you add a path from north to south, but you do this in a free way. So like everything else is just I mean, if you want a precise thing, then really what we're doing is you're taking an homotopy push out. I mean, you're a mathematician, so maybe this is the thing that makes more sense. Yeah.
Is this like a 2-point compactification of space?
Let's say I don't know. Okay, Steve is shaking no, so I'm say no. Right. Okay, and so maybe at this point, if you have never seen this before, it's not clear why you would care about this. Okay, so maybe I give 2 examples to show why you would care about the suspension in the first place. So let's do a few examples. Let's do the suspension of the 2-point type. Okay, so what does this look like? So I have my 2 points, maybe I'll label them 0 and 1. And now I have, in the suspension, I have north and south, right? And now I add a path like this, and I add a path like that. Okay, what do I get? I get a circle. Right? This looks like, I mean, just pictorial. Yeah? That's a circle. Okay. So S1. Now that's the notation for the circle. So this thing is circle. Now, the next picture is even better. So now I suspend the circle. So, okay, what do I get? I have north, I have south, and now I have my circle here. And now for any point in this circle, right, I'm going to add this path here. Okay, I hope it's clear what, right? You're going to get a sphere. Yeah? So this thing is going to be the sphere, and then you can get higher spheres if you care about this with them. Okay. So maybe, yeah, I mean, like I was saying earlier, you can write this down like in this higher inductive syntax. You can put that into a computer assistant like cubical algebra or something like that. But mathematically, we're thinking about these spaces. Okay, so that's what's happening. So hopefully, you at least care about spheres, and then you care about suspensions. Okay. So put another way, actually, so taking suspensions increases connectivity. In particular, all the spheres are going to have higher connectivity, right? Because the spheres you get by just iteratively taking suspensions. Okay, that was a picture. That means that now it's time for definition. Okay, this is maybe the most challenging. Maybe this is the only part where I look at this. I mean, it's not terrible. But, have to know a little bit. So, let me put this here maybe. So you can, if you want, if you've never seen it before, you can take it as a definition. If you have seen it before, you can take it as a proposition. So a type A is said to be K connected. So here, let's say that, okay, for technical reasons, K is some natural, like K is an integer starting from -2, okay, but I mean you can kind of think from 0 1. I will give an explanation in a second. Is K connected if for all K times B, the constant or the constant map, so this is B goes to A goes to B, so this thing takes B, takes an A, outputs B, just completely ignores the A component. This map is an equivalence. Okay, let me explain this. The idea of the K-types is, so Emily yesterday talked about these infinity groupoids where you have elements in your space and then you have paths between those elements and then you can have paths between those paths and paths between those paths and higher and higher and higher and so on, okay? So that's the picture you have in mind is you have some point and then you have some paths like that and then maybe in between those you have a path and then between that you have a path and it goes up like that. Now, you could say, what if this process stops at a certain level? And that's exactly what this K-type notion formalizes. Okay, so an example here is that a zero type, so zero types are sets. So sets in this system, they are just types which have elements, but they have no interesting paths between these things, right? So natural numbers, or like this 2-point type, right? You just have the 2 points and that's it. And then you can go a little bit higher. So for example, a 1 type is a type where the paths form a set. So for example, in the circle here, this is actually an example of a 1 type because the paths in this space, if you, again, intuitively, what is a path in this space is just the number of times you kind of go around the circle. And so you can go like counterclockwise a couple of times and then anti-clockwise a couple of times, and you add that all up and you get an integer out of it, which just says the number of times you went around that thing. But the point is that this is kind of cat, and then a type is k connected if for such, like basically from the perspective of a k type, A is completely uninteresting, because the only maps out of A into such a type, well, I mean, they're all the constant maps. Okay, so this is the intuition. So let's say from the point of view of K types, K connected types are trivial. In particular, this type, the circle, from the point of view of zero types, from the point of view of sets, this type or this space is completely uninteresting. Because a set doesn't have the capacity to detect this loop. It just has elements, and if you just look in a real sense at this space, it just has a single element. Yes, it has this very interesting loop, but the sets won't be able to detect this at all. So this notion makes that precise. In fact, an alternative definition is to say, if I take A and I K truncate it, there's a universal way of making my type a K type, then actually I get the trivial type. Okay, so that's the idea to have in mind. Okay, this is the hardest bit. And after this, I get to illustrating the technique, but I didn't want to really lie to you, and I wanted to make it self-contained, or try to at least. And moreover, I needed to be in a situation where I reduce this statement to a statement of the form showing that a certain map is an equivalence, right? And now I can do that because I have to show that this constant map is an equivalence. Okay, so that gets me in position. Right, okay, so let's try to do this. Okay, let me think about the layout of it. Okay, well, the image is not very good, is it? I mean, I have to use the wet eraser and then we have to wait, so let me do it here. Okay, so let X be a K-connected type. And we have to show that the suspension of X is then K plus 1 connected. Okay, that's just what I really meant when I said that the suspensions increase connectivity. Okay. Right, so I have to show that something is K plus 1 connected. So I have to show that for all K plus 1 types, this constant map is an equivalent. So I'm going to take the K plus 1 type. Okay. And now I have to show that Y suspension of X into Y, I call this F, and this is the constants map, is an equivalence. Okay. And then I'm not going to do this directly, because this would involve taking such a map, producing a point, and then at some point I would have to show that doing the round trip, which would, one of these round trips would land me into this function space and having to prove that these functions are equal. That's kind of annoying to do. So instead what we do is we consider this. We have Y, suspension X into Y, and now I consider another map here. So this is F. And this map evaluates this function at the North Pole. Okay, this type always has these two distinguished points, the North Pole and the South Pole, and I just take the function and I evaluate it at the North Pole and I get a point into Y. Okay, now if you take, if you look at this map here, this just ignores the first component completely and always like outputs the y that you start with here. So this whole thing, this composite, is definitionally equal to the identity. Okay, that's an immediate calculation, and in the proof system you just say it's left all done. Okay, so we know that the identity is an equivalence. So in order to prove that f is an equivalence, I just need to show that evaluation at the North Pole is an equivalence. Okay, so by, let's say, approach 3, and also I didn't, so I'm going to put here this one, I didn't cheat you. This was really obvious that this commuted, so by approach 3, it suffices to show that evaluation at the North Pole is an equivalence. And now I will do this. And for this, I'm actually going to use the second technique, or the second approach.
I think you want to use this under there.
Okay. Under there.
Yeah.
Okay. Okay. That's some effort. Thanks. Should at least get us through the first bit. Okay. Right. So I'm going to use the second approach for this. For evaluation at the North Pole. Okay. So I just start out with the domain of this map. So that's just this, and well, then we get going. So okay. How should I think of this function type? Well, a function like that, what should it do? It should give me 2 points in y, at least, because this has a North Pole and it has a South Pole, and so if I evaluate those, I'm going to get 2 points in y. So that's where I'm going to start with. So I have a y0 in y, and I have a y1 in y. And moreover, whenever I have an element in x, then I need, because the points in here, they're going to, where's the picture? There it is. Right, so these 2 points, they're connected whenever I have an element in x. So that same needs to happen in the type y. Yes. So here I have a map from x into y0 equals y1. And in fact, if you like, this is really the universal property of this type. It completely describes what this thing does. This map is an equivalence, and just to be very explicit here, let me describe what this does. So it takes a G, and over here we evaluate it at north, we evaluate it at south, and then if I have an X, then, well, there is an associated action. Maybe I write square bracket G for the map, G for, I'm going to have to explain this. So merit X is the meridian at X, which is what we call these things here. Meridian X, just to give that a name. Okay, but at least thinking about the picture, what does it mean to put all of this structure onto Y is basically just doing that.
That's an eliminator, right? The eliminator.
Second?
Is that like the eliminator or
yes,
whatever?
Yes, if you like, yeah. Okay. So I have this equivalence.
And why
You're looking
is that
puzzled.
equivalence?
Did I mess up somewhere?
No.
Okay, good. I was getting worried there.
Why
Okay.
is it an equivalence again?
Right, so just think isomorphism, let's say, if you want. But I mean, the point is of all of this is that it doesn't. I mean, take this for granted for the moment, and then I show how to do the rest. Okay. Now there's one more. There's one fact that we need to know. Another basic fact, but which is that so this type here, this thing was a k+1 type, and that means really by definition of k+1 type that this thing here is a k type. So when you look at the paths, you go down one, right? Just like with the circle, the paths in the circle is a set, so you go down one level. Okay, but that's good because this guy was k connected. Right, so now I have a map from over here. I have a type of maps from a k connected type into a k type, but I know. Right. So if I am in that situation, then I know that all of those things have to be constant. So I get an equivalence here. Like that. Okay? And
here you are answering my question. It's like, can you do this transformation easily?
Yes, yes. Okay, so I explain now. So what is the map here? Basically, if you have an equivalence on those things, then on the sigma types, on the dependent sums, it's functorial, I mean, on those equivalences. So if you have an equivalence there, you can just transfer it. And what does it do on the map? Well, it takes a y0, it takes a y1, and it takes this function here, this, let's say, alpha, and, well, here you keep it untouched, and then you apply the equivalence. So here you get y0, y1, and now here I get something that I can't be bothered to compute, but it doesn't actually matter for the end result of the argument. Because I know that the constant map is an equivalence, right? So I know what the map going from here to here is doing. It's taking an element here and just always outputting that. I don't actually know what the other map is doing, but I don't care, because again, I'm going to project all the way down, and that's going to be fine. So that's the next step, because now, well, over here, look at this. I had this very basic equivalence saying that if I pair up the things equal to some element, then I'm just left with this trivial type. So actually, I can just completely ignore that, and I just get a y out. So this is projecting P01. It's just taking y0, y1, and something, and producing the y0. Yeah? And so this is an equivalence by that basic building block that I have over here. I mean, if you want, you can spell this out a bit. You get more formally. I guess you would get y times 1. Okay, and then this is equivalent to y. Okay, and now over here, I'm going to put evaluation at the North Pole, and you can actually check again that this diagram commutes definitionally, because if I start with a map here, and I evaluate it at the North Pole, okay, that's what this thing is doing. Over here, I evaluate at the North Pole, I evaluate at the South Pole, and I do some other stuff. But, okay, then I change that third component, but in the end, it doesn't matter anyway, because I project everything away, and I'm just going to be left with this thing at the very end. So this diagram commutes definitionally, I don't need to do any work. And so I decomposed this, or reconstructed this map as a series of equivalences, namely this equivalence, that equivalence, and this equivalence. So this thing is an equivalence. Now, and then, well, then here already we reduced this to evaluation of North Pole being equivalence, and again I get an F actually equivalence, and I finished the proof. So let me make a few remarks here. The first is that, of course, it's possible to take all of this and kind of boil it down to a direct proof that F is an equivalence, right? And maybe that's good enough when you're just writing a paper, but you wouldn't want to do this in Proof Assistant. But one of the things that I actually find since I started to formalize these things is that I start to prefer these kinds of proofs anyway. Because in some sense, conceptually, they're a bit clearer, you know, they really show what is going on. And I don't have to feel, you know, I don't have to feel guilty for not checking that some diagram commutes. I sort of set things up in such a way. The other thing here is that there really is a heuristic at play, which is where you try to make, as I said earlier, but here we have a really an example where you try to point everything to the most simple type around. Okay, so here I have this triple, right, 2 sigmas, and then this complicated function space, but I point the diagram in such a way that everything in the end points to this simplest possible type down here. Yeah? That allows me to then do as little checking as possible. Here it's really good because things actually definitionally commute, but it may be that the proof for commutation is a little bit, like you actually have to do a little bit of work, but still, by making the type as simple as possible, you reduce that amount of work to like the lowest possible amount. Now, yeah, that's something a little bit strange here going on, maybe, in the sense that really the definitional equalities that you have in your proof system now really start to impact the kind of proofs that I start to write. So whether or not maybe that's desirable is maybe up for debate, but at least I found that it's something that is really quite convenient in formalizing these things. And I think it's, like I said, it's not extremely deep to use this technique. I mean, 3 for 2 for equivalences is not a deep fact by any stretch of the imagination. It's a very basic thing. But somehow it's not immediately obvious that actually you can make use of this when you formalize these things, right? The naive thing to do is just to construct this inverse and get going with it. And then maybe you do a little bit better by doing this technique. But I think even this. So since I learned this, I basically try to set up all the proofs like that. Or if I have to do a bit of work, I stop and I think, okay, can I do a little bit better here? Because sometimes formalization, I mean, can be a lot of fun, can be kind of addictive. But then it's challenging when you're doing that to kind of stop and take a step back and say, am I really doing the right thing, or am I just powering through and creating more and more problems for myself, right? Okay, I'm not going to need the full hour, but I think that's a good thing, right? Because the sun is out again.
Yeah.
But if you have, so this should also be treated, this is the final thing I'll say, it should be treated as an invitation to, so if you want to know a little bit more about synthetic homotopy theory or homotopy type theory, please come find me. I'm around for another week and a half. And if you want to talk about definitional equalities or formalizing independent type theory, I'll also be very happy to chat. So thank you very much.
Questions?
You said that 3 for 2 wasn't a deep fact, but
Yeah.
you say you have a totally generic proof of 3 for 2, then do you? Which you just pick up and keep reusing, or?
Yeah, I mean, it's, well, I'm not saying it's completely straightforward to prove maybe, but I mean, it's a basic fact in the sense that you prove it early on and then...
Okay, so you can prove it in full generality is the point, then just pick it up and keep reusing it, right?
Yes, exactly. The other thing is that, I mean, there is in some sense, I mean, being an equivalence is what you call a proposition, so there's no, it doesn't really matter how you implement this proof as well. There's, any proof will do, really. Whereas these commutativity proofs, I mean, there may be actual content in the identity types in the path, so there actually matters not whether this thing is definitional or not. Steve?
Have you thought about the connection under univalence to paths in the universe and normalizing those terms? Because in the computational setup that you keep collecting,
Right.
These equivalences are paths in the universe,
Right.
and have normalization algorithms for those. And so, you know, it might be kind of normalization moves.
Right.
And then the definitional ones factor out.
Yeah, that's interesting. I haven't thought about that. Actually, your question reminds me, I want to make one small point of order here, which is that this perspective here was already in, where I kind of picked this up from Martin Escardo's type topology. ACTA development. And the third one, and I'm very sorry actually, I forgot to mention it. So the third one I picked up from ACTA Unimath. And in particular the work that Egbert Rijke did on this. So I don't think it's mentioned explicitly anywhere there, but like the infrastructure is set up in a way to support this kind of reasoning. And so all I really wanted to do was to kind of bring that out in the open and talk about it a little bit, rather than it sort of being this practice that people do, but they don't really talk about doing this, you know, you just kind of have to figure it out for yourself. But yes, so thank you, somehow you reminded me of mentioning these two things, so thank you for that.
Is a 6 for 2 ever useful?
I don't know, maybe.
What's 6 for 2? Isn't that just...
Yeah, we have, it doesn't need to be like a triangle. If you have a chain of 4 maps and the 2 overlapping ones are equivalences, then everything inside this.
I think it could be, but on the other hand, I think when you're formalizing, it's often helpful to break down these things into little lemmas or little facts anyway, which is also really happens to be the style of ACTA Unimath. So then it kind of helps to put everything into little triangles, right? That's also how I presented things here. I first built this sort of degenerate triangle with the identity map here, but I could have presented this whole thing in one big diagram where you kind of inline this argument, right? But often it's easier to kind of break it down as well in the proof assistant.
I would also like to add also the coupling mods to here, because I mean, this kind of, especially the second approach, is often used to show univalence for categories. You also
using the displayed machinery, I guess.
Yeah,
in particular. Yes. Yeah. Okay. So I should stress that this is certainly not the only point where I picked up this point, but this is the one that I used a lot.
It was somewhere movement, not like a question, but
it's cute that you are actually like kind of triangulating the space of types to prove things.
we seem to have exhausted questions, which is a good sign that we should have coffee.
And cake.